studying the schematic diagram and wiring all the components to the STM32 board. Then, we configured the GPIO pins for the motors, encoders, servo, and sensors. Next, we calibrated the motors, tuned the PWM signals for precise speed control, and used encoder feedback to track position. We applied PID control to stabilize motor speed and achieve smooth, consistent motion even on uneven surfaces.
We also set up the built-in gyroscope and servo motor to ensure accurate orientation and smooth steering. The gyroscope enabled us to specify at which angles the robot should turn, and the servo motor allowed us to adjust the turning radius. Lastly, we set up serial UART between RPi and STM for real-time communication.
Hi guys, we are the RPi
and the ImageRec team.
In F1, victory depends on the seamless link between the driver and the engineers. For our car, the Raspberry Pi is that link, the central hub connecting the STM controller to our race algorithm. The Pi runs multi-threaded processes to handle commands from the Android app, path data from the algorithm, and visual feedback from the car. Through a UART team radio, it sends precise instructions such as forward, right, left, or back to the STM, which executes them instantly. Mounted on the Pi is our camera, the car's eyes. It streams live video to a trained YOLO model that detects track markers and arrows in all lighting conditions, converting detections into movement commands in real time. Together, the Raspberry Pi and STM coordinate like driver and pit crew, keeping the car perfectly on its racing line.
Hi, we are the Android team.
I'll now be walking through a demo of our application. On launch, an animated Lottie splash screen greets the user before being brought to the arena map grid. To start, users have to connect the app to the RPi via Bluetooth, with connections fully handled in-app. A message log tracks all communication for testing and reliability. Once connected, the obstacles can be configured on the map. It can be placed by dragging and dropping in place, manual input for more precise positioning, and directions can be changed by swiping the screen to the intended direction. Updates and deletes can also be easily achieved. Quick buttons to randomly generate obstacles or reset the map is also implemented to ease testing. A D-pad is included for manual driving. Holding the forward or backward button moves the robot continuously until it's been released, and the left or right button triggers a 90-degree turn. Finally, a task selector and timer is also included to track each run and signal task start to the robot.
Moving on to the algorithms.
We use the combination of A-star pathfinding and traveling salesman problem optimization to find the most efficient route. We use A-star pathfinding to calculate routes between all position pairs and traveling salesman problem dynamic programming to determine the optimal visit order for all obstacles.
While our algorithm performed well in simulation, deploying it on the physical robot revealed several challenges. We experimented with increasing the expanded cell constant. This reduced collisions but also made some areas unreachable, which limited image detection opportunities. We also tested reducing the turning radius to enable tighter maneuvers, but due to hardware limitations, this was not feasible. Ultimately, these adjustments worsened overall performance, so we reverted to the original configuration.
When precision met reality, chaos followed. Debugging and tuning for a flawless run. Vision team, abort, abort, abort!
And there we go, a collision has happened. Will they recover? Will they make it?
Boards fried, sensors drifted, code crashed, but the crew never stopped. What followed was an extensive phase of systematic integration and iterative debugging, until...
Just stop, please stop, guys, stop.
Go in a bit more! Yeah!
We received $80 worth of vouchers as our prize for being the top team in our
Okay.